Hello students, in continuation with my lecture series on AKTU Energy Science and Engineering for Btech second year students, now I will be continuing with my lecture on Unit 1, Energy and its usage. In my previous lecture, I told you about the different types of energies, potential energy, kinetic energy, the important energy units and conversions in MKS, CGS and FPS system of units, and a brief about electromagnetic energy and total energy being equal to the sum of kinetic energy and potential energy. Now today we will discuss storage, conversion, transmission, and radiation. Storage. Energy will obviously be stored before it can be used to do work. You store energy in the form of eating in your body, then whole day you do physical activity and utilize that energy that had been stored in your body. In a very similar manner, there are many practical applications which prove that energy is stored, like solar panels. They store the solar energy during daytime, and at night that energy stored is used for various purposes like heating of water, running of power systems, etc. In physics lab, capacitors are used to store charge, so they can also come under the heading of storage. Once this charge is stored in the capacitor, it can be used wherever you require an electric current due to the flow of charges. Similarly, electromagnetic energy, which we get from the sunlight. Now, first, let us understand this spectrum. This has once been asked. Discuss electromagnetic spectrum and energy in detail. So, first, we will see the electromagnetic spectrum consists of which all rays of light. Cosmic, remember them like this, C, G, X, U, V, I, R. That way it will be very easy for you to remember them. C, G, X, U, V, I, R. Cosmic ray, gamma ray, X-ray, ultraviolet, visible, infrared, and radio waves. Here you can see that they are going from the lower frequency. Obviously, V is equal to F into lambda. I have given this formula here. So the relationship between frequency and wavelength is inverse. So lower frequency to higher frequency, then long wavelength to short wavelength, low quantum energy to higher quantum energy. You can make this diagram in your 10-mark answer in order to get marks, and just if you can't remember this scale, just show how it goes from lower to higher. The different parts of electromagnetic spectrum have different effects upon interaction with matter. Starting with the very low frequency radio waves, the human body is quite transparent to it. You keep radios across your for listening to music, etc., and they are harmless. In the lower ultraviolet range, all the ultraviolet radiations from the sun are absorbed in the thin outer layer of human skin. Each portion of the electromagnetic spectrum has quantum energy appropriate for excitation of certain type of physical processes. The energy levels of all physical processes at the atomic and molecular levels are quantized. This you will right now study in quantum physics, where you remember the formula E is equal to n square h square upon 2 pi, where you remember that the formula for energy existed in quantum multiple, or charge Q is equal to NE. So in the very first unit, the details for this are there. If electromagnetic energy is absorbed but cannot eject electrons from the atoms of the material, then it is classified as non-ionizing radiation, and it will just heat that material. So what are the different forms of energy which you are going to write for your 10-mark answer? Mechanical energy, thermal energy, nuclear energy, energy, chemical energy, electromagnetic energy, gravitational energy, kinetic energy, potential energy, whichever you remember. Now, most important part of Unit 1. This question has been asked every year since the time the syllabus came into being. Either you are asked the importance of quantum mechanics, or you are asked proof that the energies exist in quantum states or eigenvalues, or you are asked to derive time independent and dependent Schrodinger wave equation, or you are asked the detail of particle in one-dimensional well. So this is very, very, very important quantum mechanics, because quantum mechanics proved that energy in free atoms can only be found in certain discrete energy states, which are known as eigenvalues or eigenfunctions, and they are quantized. That is, only certain photon energies are allowed when electrons jump down from higher level to lower levels, producing the hydrogen spectrum. Quantum mechanics is an important tool to understand at the theoretical level the electronic structure of chemical compounds and the mechanism, thermodynamics and kinetics of chemical reactions. That is why the quantum mechanics is very important to be studied before we start studying energy in detail in Btech second year. So quantization, this word, if you remember, charge is quantized. Q is equal to NE, where N is 1, 2, 3, 4. That means it exists in quantum multiples. Or electron, which is orbiting around the atom, is existing into certain discrete values like N equal to 1, N equal to 2, etc. So quantization of energy refers to the fact that at subatomic levels, energy is best thought of as occurring in discrete packets called photons. Photons come in different denominations according to the formula E equal to H mu or E equal to NH mu, where N is an integer equal to 1, 2, 3, 4, etc. Now we know that light has a dual character. At times it behaves as a wave and at times it behaves as a particle. The combination of this dual character of light was shown by de Broglie's wavelength, which stated that lambda is equal to H upon P. So what happens is that, stated by Einstein, the energy of light is concentrated in small bundles called photon, and light is behaving as a wave and as a particle, giving rise to the dual nature of light. This property of light is known as wave-particle duality, where we assume that a wave is traveling with large number of particles inside it, and we refer to this as matter wave. Each particle in this wave is having de Broglie wavelength lambda equal to H upon P, where P is momentum. Now, when this wave is traveling, we need to define a factor which will explain me the motion of this wave. So we take up an incidence where we call it wave function. This wave function is telling me the properties of this matter wave, which is consisting of large number of particles. Since the number of particles is very large, wave function, in order to be acceptable for my quantum physics, should be normalized. That is, the particle is necessarily integral of this particle over the whole space must be equal to unity. It should be continuous so that my wave is in motion, and it should be differential. After I get these necessary conditions for my wave function to be acceptable, that is, quickly let me tell you, it should be normalized, it should be differential, and it should be finite. Conditions necessary for wave function to be acceptable. This has been asked in section A. What are the necessary conditions for wave function to be acceptable? It should be normalized, it should be single valued, it should be finite, it should be continuous and have a continuous first derivative. Then I go in to write this matter wave in the form of equation so that I can utilize it to solve a problem. So there are two equations of Schrodinger, time independent and dependent. Both are important from your AKTU exam point of view, and they are asked for 10 marks in section C. Derive Schrodinger time independent and time dependent wave equation. I have given you two methods for deriving this equation. I will explain you the shorter and easier ones. So de Broglie waves or matter waves, they are given by lambda equal to h upon p, and this condition is there in your syllabus of particle in one-dimensional box. So first I will derive these equations in a very easy manner for you. See, this equation lambda equal to h upon p. Lambda is showing me the wave aspect of matter wave. H is a constant known as Planck's constant, and P is showing me the particle aspect of my matter wave. You can write like this only in your exam. Remember, this is a theoretical paper where you need to write a lot in order to explain the question. Numericals of 1 or 2 marks can be asked on this equation, and the other forms of this equation are lambda equal to h upon under root 2 me, lambda equal to h upon under root 2 mqv, where v is voltage, q is the charge. Lambda is 12.28 upon under root v. Answer comes in angstrom. Numericals are important on this part. What are the properties of matter waves? Matter waves are not electromagnetic waves. They are generated only when the material particles are in motion. Velocity of matter waves is greater than the velocity of electromagnetic waves, and matter waves are associated with particles. So now, before I begin to derive Schrodinger equation, let me once again tell you, imagine a wave traveling like this with large number of particles, each particle having de Broglie wavelength, and probably because the particles are very large, so I will not be able to give the exact answer for a question. So I will say probable, or I will use the word probability. So this is combining wave nature and particle nature. It is matter wave, and I am now going to derive an equation in mathematical form to help me explain the motion of this wave. Now, wave equation. The equation of wave traveling in the direction of increasing x, general equation is given by y is equal to a cos 2 pi mu into t minus x upon omega, where a is amplitude of vibrations, mu is my frequency, speed of waves is omega, which is traveling in the x direction. I know that omega will be equal to mu into lambda. So I put this value here, this omega value in this expression here, and I get the wave equation in this form. I can write this form directly also, both are correct. Now, there is another equation. I can write it in terms of this wave constant number k. So omega is equal to mu into lambda. So I multiply numerator and denominator by 2 pi. It makes no difference. And once I get 2 pi by lambda, this is known as wave number k. So I get 2 pi mu. This is linear frequency. It will be equal to angular frequency omega, and 2 pi by lambda is wave number or wave constant equal to k. How did I get it? Omega is mu into lambda, and I have multiplied and divided by 2 pi, which I can do mathematically, and I have written it in terms of wave number. Omega is my angular frequency, which is equal to the phase velocity. You can put a bar here so that you don't confuse this omega with this omega, or you can even use a U symbol here. And this is angular frequency, k is 2 pi by lambda equal to wave number. So group velocity for a group of waves, group velocity, the word group means that these large number of particles are moving in a group. So I need group velocity. It is going to be given by d omega by dk. So I will differentiate this expression in order to find Schrodinger wave equation. This is a very easy way of reaching Schrodinger equation. Otherwise, Schrodinger equation becomes very complicated. So U is equal to d omega by dA. The group velocity may be greater or lesser than the phase velocity. Phase velocity will be defined for those particles which are traveling in the same phase. It depends on the manner in which the phase velocity varies with wave number. And also in terms of frequency and wave number, I can use Einstein's expression E equal to h mu, and I can equate E equal to h mu to E equal to mc square. Both are the different forms of energy, and I get mu equal to mc square by h. This mu value I can put here in omega, and I get cancel, m gets cancelled, h gets cancelled. I am left with c square upon v. So omega into v is equal to c square. Relation between phase velocity and group velocity is equal to square of the speed of light. One numerical example I have given, which is on de Broglie wavelength. Very easy. Find the de Broglie wavelength associated with the proton moving with a velocity equal to 1 upon 20th the velocity of light. Lambda is h upon p. P I can write as mv, momentum is mass into velocity. Velocity has been given to me as 1/20th of the velocity of light. So 3 into 10 to the power of 8 upon 20. M I have been given proton's mass is 1.67 into 10 to the power of minus 27 kg. H Planck's constant 6.6 into 10 to the power of minus 34 joule second. Putting these numerical values, I get the value for de Broglie wavelength lambda. Few derivations important for section B, which you can see. Now I begin by time-dependent Schrodinger equation. See, wave function of a freely moving particle in x direction is given by phi is equal to a e to the power of minus I omega into t minus x by v. Omega angular velocity is equal to 2 pi into angular frequency equal to 2 pi into linear frequency, and velocity is equal to frequency into wavelength. Putting these two values in this expression above, it becomes phi is equal to a e to the power of minus 2 pi I bracket mu t minus x by lambda bracket closed. Also, from Einstein's mass energy equation, E is equal to h mu and h bar is h upon 2 pi. So h becomes equal to, if I cross multiply, 2 pi h bar, Planck's constant value. So my de Broglie wavelength becomes lambda is equal to h upon p, which is equal to 2 pi h bar upon p. Putting these values in my expression of wave equation here, I get wave function phi equal to a e to the power of minus I upon h bar into e t minus px. Now, since this wave function is an acceptable wave function, that means it is normalized, it is finite, it is differentiable, I will differentiate it twice with respect to x, and I get del 2 phi by del x2 equal to minus p square upon h bar square phi. And once again, I differentiate it with respect to time, and I get del phi by del t equal to minus I e upon h bar phi. For small speeds, total energy is the sum of kinetic energy, K is half mv square. Instead of v, I can also write it in terms of momentum P, because P is equal to mv and potential energy V. So I multiply both sides of this expression by wave function phi, and I get E phi is equal to P square phi upon 2m plus V phi. And equations from above equations here, del 2 phi by del x2 was equal to minus p square by h bar square phi, and del phi by del t was minus I e upon h bar phi. Putting both these values here, I get the expression for time dependent Schrodinger wave equation equal to I h bar square del phi by del t equal to minus h bar square upon 2m del 2 phi by del x2 plus v phi. Now, two questions are asked, time dependent and time independent. Please remember, this is not tough to derive. Only thing is that I am just substituting various terms in a much easy manner in my expression for wave equation. I am differentiating it. I am writing the expression for total energy and writing the Schrodinger equation. If I want to write this expression in 3 dimensions, then I will just replace my del 2 phi by del x2 in 3 forms, del 2 phi by del y2 plus del 2 phi by del z2, and using the symbol del equal to del by del x plus del by del y plus del by del z, I get my Schrodinger equation as minus h bar square upon 2m del square plus v into wave function phi equal to I h bar del phi by del t. This equation is used to explain non-stationary phenomena such as electronic transitions between two states of an atom. Time independent Schrodinger wave equation, very easy. What you do in this case, once again you write down the expression for wave function phi equal to a e to the power of minus 2 pi I by h into et minus px. Now separate this into space and time dependent parts. See, this first expression, I am writing it as a e to the power of 2 pi I px by h, and the second is in the time independent form. What I will do is I will differentiate this with respect to x twice, and I get del 2 phi by del x2 is equal to d2 phi by dx2 e to the power of minus 2 pi I e t by h. Again, I differentiate it with respect to t. The same thing I did in the previous equation. And then I put these two values in my time dependent equation here, and I get my expression for time independent Schrodinger wave equation equal to del 2 phi by del x2 plus 2m by h bar square into e minus v phi equal to 0. In 3 dimensions, this expression becomes del 2 phi by del x2 plus del 2 phi by del y2 plus del 2 phi by del z2 plus 2m upon h bar square into e minus v phi equal to 0. So quickly I revise what I studied in today's lecture. I studied that de Broglie equation gives the relation between wave nature and particle nature. I studied that wave function, in order to be acceptable in quantum physics, should be normalized, finite, continuous, and differential. I studied that relation of multiplication between phase velocity and group velocity is equal to square of velocity of light. I studied time dependent Schrodinger equation minus h bar square upon 2m del 2 phi plus v into phi is equal to I h bar del phi by del t. And I studied time independent Schrodinger wave equation del 2 phi by del x2 plus 2m upon h bar square into e minus v phi. Thank you.